Okay, welcome, Calc AP students. So basically, I'm just going to be working through this week 1 homework packet, and it is extremely similar, like problem for problem, similar to the homework packet. So if you're watching this, you're on the right track to doing the homework packet well. I feel like you could literally work through the homework packet as I work through each problem and kind of just like translate the same strategy and like be reminded of the same ways to solve each problem and then do the homework packet perfectly. Okay, so let's get started. So this first problem says compute the average rate of change of each function over the given interval. Leave your answers as fractions in a simplified form. Cool. So the first thing that we remember is that average rate of change. All right, average rate of change as AROC is equal to the slope of the secant line. Remember, the secant line is literally, let's say we have some function that looks like a parabola, right? A secant line literally just connects the function at 2 points. So like it'd be there, and then the slope of this tells us the average rate of change between those 2 points, which makes sense. It just connects them and tells us on average, the function goes from here to here in the slope. Okay, so the equation for this is f of b minus f of a over b minus a, and this might be kind of confusing, but it's really just rise over run. So we're finding the difference between this point and that point. So change in y over, and then b minus a is between here and here over change in x. So this is a, this is b, so we would have f of 4 minus f of 1 over 4 minus 1 is equal to, I'm just going to plug in f of 4 is, I'm going to plug that in here, right? I'm going to plug that in for x there. So 4 squared, 16 times 2 is 32, minus 8, 24. So we get 24 minus f of 1. We're going to plug in 1 here. So 1 squared is 1 times 2 is 2, minus 8 is negative 6. So minus negative 6 over 4 minus 1. We're going to get 20. Well, 24 minus negative 6 is going to be 30 divided by 3 is equal to 10. So the answer is just 10. So for this one, basically we would have some graph. I'm not exactly sure what this looks like, but probably some type of parabola. And then the slope is 10. So we would say like be pretty positive. So the secant line probably looks something like this. Right? That was bad, but it connects the 2 points and it's very positive, and the average rate of change is 10. Okay, cool. Moving on to review week day 2 concavity. So this is, I'm just gonna do one like really complex problem that incorporates all the elements that we need to know. I know the problem in the packet is like simpler, or well, there's more problems, but each one should be easier. So concave down and decreasing over the interval from negative infinity to 0. So negative infinity to 0 is like from way over here to 0, right? So on this interval, we're concave down. Well, what does that mean when we're concave down? That means our function, right? The slopes as we go from left to right, as we go from left to right, the slope must be decreasing. The slope of the tangent line you can think of is decreasing. So we have a tangent line here, it's positive. Over here, it's still positive, but it's decreasing, right? And then even here, it's decreasing even more. So we know this is concave down. That's cool. What I just drew is concave down. This type of shape is concave down. And it's also decreasing. Well, decreasing means that it's like, just in general, it's going down, right? It's decreasing. So like, this is an increasing function, right? This would be a decreasing function. It's going down. Basically, we need to draw this shape, but going down. So it'd be like this, right? Because notice, well, like that. So notice it's still concave down, right? Because our slope, like that, right? And then go to the right a bit, and it's decreasing. The slope is decreasing. And also the overall function is just going down. So we can just draw our function like this. Sorry, I'm not very good at drawing, but from negative infinity to 0, it is decreasing, and concave down. Cool. And it is concave up and increasing over the interval. So concave up means, again, the function has to, let's just draw the tangent line. So the tangent line starts off, let's say like this, and then it increases a bit more, increases a bit more. So you can kind of see the function be shaped like this. It's basically, it's curving up, if you want to think about it in that way. In contrast, if it's concave down, let's say it starts off like this, and it goes like this, and like this. So like this would still be concave down, right? Because each tangent line is decreasing. We want the opposite of that. We want it concave up and increasing. Well, that should be pretty easy. Like we'll just draw it concave up, right? Again, each of the tangent lines, the slope is increasing. You can very clearly see that. And overall, the function is also increasing because it's going up. We could draw a function that's concave up and decreasing. That would look like this, right? Because notice this is still, even though it's decreasing, don't be fooled. It's still concave up because the slope is very negative. It's still negative, but it's increasing. That's what matters for concavity. And then it's increasing. You see it goes from negative to slightly less negative to almost zero. So it's concave up. But in this case, we want an increasing function. So it looks like this. So that's all you have to really draw for these. Cool. Now we're on to week 1, day 1, graphical limits and limits by substitution. So this is just graphical limits. So evaluate f of 0. So f of 0, we literally just plug in 0 to the function, right? This isn't asking us for a limit or anything. So we just go to 0, let's plug it in. And look, it's a filled in hole at 3. So it is equal to 3. Notice that this hole is empty. So we know that the function at 0 isn't actually at -1, it's at 3. Cool. Now limit of f of x as x goes to 1. Remember, when we look at limits, any limit, right, what it's really talking about is a two-sided limit. So where does this function approach as it goes to 1 from both sides? Well, from the right, it's approaching 1, and from the left, it's also approaching 1. And what we care about is where it's approaching, right? You'll notice that the actual point is down here, but that doesn't matter. We're looking at limits. We're looking at where it's approaching. And it very clearly is approaching 1. So the answer is 1. And again, the left and right limit must approach the same point. If this function was somehow over here, if it was approaching this point, then the limit would not exist. Okay, so the limit as x approaches 0 of f of x. So same idea, two-sided limit. Let's look at as it approaches 0. 0 is right here, right? So from the right, we're approaching 3. From the left, oh man, we are approaching way down here, -1. So they're approaching different points. We just covered that. If they're approaching completely different points, then the answer is does not exist. The two-sided limit does not exist. The answer is does not exist. Okay, well, let's look at the next problem, which is the limit of f of x as x approaches 0, but there's a plus symbol. So that tells us we're approaching from the right. So we just looked at this, but we're only approaching from the right this time. We don't care about this side. That does not matter to us. So approaching from the right, we're going to 3. Cool, our answer is 3. Awesome. Okay, 2, evaluate the following limits as a box. Evaluate the following limits and box your final answer. Okay, so hint, you will have to do some algebraic manipulation in order to solve this. That's a pretty good hint that we're gonna have to do some algebraic manipulation. When we look at this, our first instinct, at least my first instinct, I see an x squared and I see something in the denominator. My first instinct is I'm gonna want to factor. And that's exactly what we're gonna do here. So we're gonna factor x -24, what factors? Like 4, 6, cool, +2, so x plus 6, x minus 4, right? The denominator is x minus 4. Easy, cancel out the x minus 4s, so we're really good. This is just x plus 6. Now, we can just directly substitute in 4, right? Just plug it in, see what happens. We don't have any issues. Just plug it in, we get 10. Because x equals 4, 4 plus 6, 10. I'm not going to write an equal symbol. So I'll make this more obvious. So the limit as x approaches 4 of f of x equal to 4 plus 6 equal to 10. Here we just factored it, algebraically manipulated it, and plugged in 4, got our answer. Okay, now we're looking at vertical asymptotes. Vertical asymptotes might be a bit confusing, but remember, okay, so the first question, function f of x is a vertical asymptote. Where is this asymptote located? If you remember from today's lecture, I think that'd be September 15th, this lecture, we determined where a vertical asymptote is, basically whenever the function just can't exist. And when does that happen? It happens when the denominator is equal to 0. So we look at this. When x is equal to -5, right? Let's say x is equal to -5. We're going to get a 0 in the denominator because -5 plus 5. -5 plus 5 equal to 0, right? So I'll just plug this in, -2 minus -5. So we're going to get 7 in the, but it doesn't matter what this numerator is. We get a 0 in the denominator. That is very bad. That means we have an asymptote at x equals -5. Well, just to clarify, you do have to remember that you have to look out for if there's any algebraic manipulation that you can do. Remember, for this problem, for this factoring problem, if we directly just plugged in 4, we'd also get a 0 in the denominator. But that's not the whole story, because we can do some manipulation so that we can show that it's not actually an asymptote at 4, because we can cancel out the denominator. In this case, there's no canceling to be done. It's already extremely simplified. So our answer is just going to be x equals -5. That is the location of our vertical asymptote. So on a graph, it'd be like at, that's not negative. So like at -5, there'd be an asymptote, right? And we kind of know how graphs, functions, act at asymptotes. They like kind of approach them and then go crazy, like go up and like go down, you know, that type of thing. Okay, so let's fill in the table below. And this is kind of just to illustrate the idea of how to solve for vertical asymptotes. So basically, let's plug in -6. You just plug in numbers that get closer and closer to the vertical asymptote. So -6, I probably should have solved this for this before, but let's see, 2 minus -6 over -6 plus 5. What is that? 8 over -1, so -8. 2 minus -5.1 over -5.1 plus 5. I'm just plugging in -5.1 for x now. So just plugging it in for x. What is that? 7.1 over -0.1. Right. So now we're going to get -71. So we can kind of tell where this is going, right? I mean, it's pretty clear. Next one, 2 minus -5.01 over -5.01 plus 5 is equal to 7.01 over -0.01. So multiply this by 100, negative, so we're at -701. Well, I think that's pretty obvious. Well, the question doesn't ask us where the limit is going to, but I think it's pretty obvious where it's going to. Here we are asked to plug in -5. Remember, -5 is our asymptote. So we can plug in -5 again, 2 minus -5 over -5 plus 5. We're going to get a 0 in the denominator, right? That is very bad. So the answer is does not exist. We cannot have zeros in the denominator ever in math. That is not cool. Okay, so -4.99, 2 minus -4.99 over -4.99. Actually, I'm going to start off at the end over here. I'm going to start off at -4. So 2 minus -4 over -4 plus 5 is equal to 6 over 1, right? So we're just going to get 6. Cool. Well, notice that it's positive. That might be interesting. That might be a sign. This one, 2 minus -4.9 over -4.9 plus 5. So we're going to get 6.9 over 0.1. Okay, so now we get 69. Cool. Finally, plugging in -4.99, 2 minus -4.99 over -4.99 plus 5. We're going to get 6.99 over 0.01. Okay, multiply this by 100, so 699. Well, I think that is also pretty obvious where this function is going. If we want to just visualize this, right? Let's say, using this graph again over here, this function, as it approaches -5 from the left, it's like, oh, it's negative, it's getting more negative, oh, it gets extremely negative. It gets all the way down to -701. So it goes down like this. In contrast, from the right, it's positive, it's at, well, positive, it's at 6, up, it's now all of a sudden at 69, now it's at 699. It goes way up. So that is kind of how we would visualize this. So using the table you filled out in part C, evaluate limit as x approaches -5 from the left. Well, -5 from the left is going here, and you can see it's going to -701. It's going basically at an asymptote. Remember, our rule for the asymptote is either going to infinity or -infinity. And if it's going to -701, we can basically bet it's going to -infinity. So the limit as x approaches -5 from the left, f of x, equal to -infinity. The limit as x approaches -5 from the right, however, so this problem coming from the right, well, it's going to 699. So what is that? That's going to be infinity. You can write positive infinity if you want, but it's infinity. Okay, cool. Does the limit of f of x exist? If not, explain why. If it does exist, then simply provide an answer. Well, it's clear that it doesn't exist because the limit of, remember, it's a two-sided limit. So this is asking us about a two-sided limit. The limit as x approaches -5 of f of x does not equal the limit as x approaches -5 of f of x from the right. So from the left and from the right, they are not equal. One goes to -infinity, one goes to infinity. You can clearly see that over here. One goes way up, one goes way down. Well, that's clearly an issue because they are not going to the same point. So does not exist is our answer for this. I'll circle our answers here. Okay, cool, does not exist. Let's see, end behavior limits. So now we're going to a different type of limit, and end behavior limits are any limits going to infinity or -infinity. Okay, remember our first step is always to isolate dominant terms. So we do that in the numerator and the denominator. So in the numerator, we have x to the 4th. Well, that's very clearly dominant. Do not forget to include the sign when we're circling. Okay, so basically this negative sign needs to be part of it. The -8, we don't care about that. It's not the dominant term. The denominator, 7x to the 4th, is clearly more dominant. Cool, so now we're going to rewrite. So let's just say it's limit as x approaches infinity for -6x to the 4th over 7x to the 4th. Now this is a polynomial function, right? And you'll see that they are the same degree of dominance. So they're just going to cancel out basically. So we're going to get -6 over 7. So this is our answer because they're the same degree of dominance. And it's a polynomial. If it's not a polynomial, then there's other issues, but they probably won't ask that. Okay, evaluate and show all work. Okay, another problem where we're going to infinity? Well, let's start off with the usual stuff. Let's isolate the dominant terms. So in the numerator, we have x cubed, x squared, and just 2. Well, that's pretty obvious. X cubed is the dominant term. In the denominator, x to the 5th, x squared, -7. Well, x to the 5th is obviously the dominant term. So let's just rewrite it just for clarity, although you don't have to ever do this. 2x cubed over x to the 5th. Now this is going to infinity, right? So, and the top and the bottom are not equal. So which one is larger? Well, x to the 5th is obviously going to be larger, so it's going to be, let's write it as large. X cubed is going to be very small in comparison as it goes to infinity. You'll be surprised, like x to the 5th, like maybe at the start, it doesn't seem like it's that much larger, but the idea with hierarchy of dominance is that as you go way to like infinity, to the super big numbers, the dominant term is always going to way dominate the other term. So x to the 5th is going to be much larger. If something's really small but something really large, it's going to be going to 0. So our answer is going to be 0. Okay, evaluate and show all work. Okay, so this is going to negative infinity. This is probably one of the harder problems on the whole packet, because negative infinity problems can be very confusing, because not only do you have to think about dominance, you have to really think about how the negative infinity plays into like the sign of the like whether the function is positive or negative, stuff like that. Okay, so let's see. Let's isolate dominant terms first. So in the numerator, x cubed and sine to the x. Remember, sine to the x literally goes like this. It does not increase. It just spends all of eternity just like blah, 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 going back and forth and back and forth. X cubed, in contrast, goes like, woo, it goes way up. It's clearly dominant. X cubed is dominant. So we can just ignore sine x, basically. Now, I don't even know how to say this, quadruple root of x. I'm not even sure. And natural log of x. Well, we learned in the hierarchy of dominance that radicals, so like square root, cube root, all of these roots are more dominant than natural log. So we're going to isolate that. I'm just going to rewrite for the sake of clarity. X approaches negative infinity, 3x cubed over, yeah, that's terrible. Okay. The quadruple root of x. Now, so what we really have to pay attention to here again is let's look at which is larger or smaller. So we have x cubed, right, going to negative infinity. That seems like it'd be pretty large. X cubed, I mean, no, like we compare it to the quadruple root. So x cubed is obviously larger than the quadruple root of x, right? So we'll get large in the numerator and small in the denominator. Cool, sounds good. So it sounds like it's going to infinity, right? We got something super big divided by something super small, something's going to infinity, but we have to pay attention to the signs. We have negative infinity. What happens when we cube a negative number? Like just to visualize, we're actually putting it in. So like 3 to the negative infinity cubed. This is negative infinity cubed is also going to be a negative number. And then in the denominator, we're doing, let's see here, so we're going to get a negative number on the top. In the denominator, we're going to get the quadruple root of anything. It's just like the square root of anything. It's always, well, it's not even going to really like, it's going to be positive, basically. If you think about it, it's like an even number in a sense. So in this case, we're going to have overall it's a negative over a positive. So we're going to have this is going to infinity. It's negative over a positive. So overall it's negative. Our answer is going to be negative infinity. Negative infinity. And remember, we only determined it was negative infinity because of the cube. We determined it was any sort of infinity at all based on the dominance, large and small. Okay, finally, we're going to look at piecewise functions. So this is basically a function. Let's say like I draw the graph from a certain place to a certain place. Maybe it like looks like this from here to there. Then from here to here, it might look like this. And then from here there to here, it might look like this. Basically, we have three different functions. That's the idea with piecewise functions. There's like different pieces. F of -2. So we're going to plug in where -2 on the function, like where it is in the domain. So at -2, notice that x equals -2, we're going to get 0. It tells us very clearly when x equals -2, well, x equals -2 here, our answer is 0. F of x is equal to 0, so 0. Okay, now at f of -1. Well, f of -1 fits into this domain, right? Well, wait, no, sorry. It fits into this domain. Because -1 is larger than -2, and anytime x is larger than -2, it fits into here. So we're going to plug in -1 into this function, 1 minus the absolute value of -1. We get 1 minus 1. We're also going to get 0, right? Absolute value of a negative number is just like the positive version of that number. So we're also going to get 0. Now the limit of f of x as x approaches -2 from the left. Okay, cool. So -2 is right here, right? Okay, but that's kind of confusing because what does it mean from the left? So that means we're going to be approaching it from even more negative numbers. So basically coming from like -100 to -10 to -3 to -2.5 to -2.1. We're coming from the left. And where would that be? That'd be from this function because this is all the values that are less than -2. So approaching from the left, we're just going to plug -2 into this function, right? So it's like, I'll try to visualize this. Let's say we have a piecewise function, right? And this is -2. And from -2 to infinity, it's like this. From the other point, it's like here. This is our piecewise function. That's not a good graph, like this. Well, for approaching -2 from the left, we're following this function. And we're like, where does it go? Oh, it goes to this point right here. That's what we're curious about, is this point right here, right? So we're approaching from this function, -2, let's just plug it in. So -3x squared plus x, I'm just going to plug in -2 for that, -3. I just plugged in -2 for all the instances of x. So -3 times 4 is -p squared is 4, minus 2 is equal to -12 minus 2 is equal to -14. So our answer is -14. Okay, last problem. Limit as f of x approaches x equals 4. Well, 4, here's the thing. 4 is like pretty clear because it just kind of fits straight into a domain. It doesn't even deal with -2 at all. So it fits in the x equals is larger than -2 domain. So we're just going to plug in 4 then, because it fits perfectly into this domain. It's larger than -2. It's not confusing like this third problem where it's asking us like -2, it's like which domain does it go in? Well, we don't even know, but the negative number tells us that we've approached from the left. So that tells us that it goes into this domain. So that's good. But this one, 4, really very obviously goes into this domain. So we just plugged in 1 minus absolute value of 4 is equal to 1 minus 4 is equal to -3. And that is our answer for the last problem. So hopefully, I just went through the packet really quickly, but hopefully you guys were able to get some good information from this. I'm going to scroll through it once really quickly in case you're at the end and you want to pause it anywhere, just look at work. If you have any questions, feel free to message me. Okay, so that should be it. Thanks everyone for watching.